This video is the start of Unit 2. We're going to be talking about equilibrium in this unit. You may have been introduced to this very briefly in your first year chem class, but there is a lot more to it that we will get into here. So to start, we need to talk about what exactly we mean by equilibrium. So a lot of times when people start out in chemistry, they think of it as reactants react and form products. Done. End of story. The limiting reactant is all used up, and then it forms as much product as it can. That is true for some reactions. Combustion, for example, follows that pattern. But it is not true for a whole bunch of them. So when you have a mix of reactants and products, we have something called equilibrium. So what equilibrium is when the concentration of all the substances, reactants and products, remain constant. And this is something we're going to be going over quite a bit today. They remain constant. Okay, it doesn't mean they have to be equal to each other. It's just that they are going to be constant. And I'll explain more about what that I mean by that as we go on. It's called something called the dynamic equilibrium, meaning that the reaction is still happening. The products are still forming reactants and the reactants are still forming products, but they're doing so at the same rate. So every time reactants are formed, products are also formed. Okay, so it goes back and forth. So we're going to be talking about both forward reactions and reverse reactions, and they'll be happening at the same time. So what we're going to talk about in this first part of this unit is something called the equilibrium constant, which we represent with a K. So equilibrium position, meaning when everything is remaining constant, all the concentrations are remaining constant, is not in the middle. And by in the middle, I mean when everything is the same concentration, all the reactants, all the products. Most of the time it's not in the middle. Okay, so all we're looking for is when the rates are equal, the forward and reverse rates are equal. And you can see this little double-sided arrow. That's our equilibrium arrow, and I'll be using that throughout this video. So we're looking for when the rates are equal, not the concentrations. Okay, so we use this thing called K, which is going to tell us the equilibrium position. Now here you have two different versions of K here. This is just, and I'll explain more about how to set this up and everything. But what this one is showing here is that the concentration of the products is smaller than the concentration of the reactants. But if that's what K equals, then this one, it just hits equilibrium when the concentration of reactants is bigger. And then you can see this one is same basic idea, but this is much smaller as a whole than this one is here, okay? So the ratio is going to be constant. They're both K, but if you have a smaller amount of products here, then you're also going to have a smaller amount of reactants here, all right? Because our ratio is always going to be the same. So you don't need to have a specific concentration. You just need to make sure they have the same ratio. That means it's at equilibrium. So magnitude, by magnitude, we mean the value, like, so not plus or minus of K, is an indication of how far a reaction proceeds towards a product at a given temperature. And we'll talk more about the temperature part in a minute. Some reactions favor the products, and they're going to have a large K, okay? So if you have a very big exponent on 10, because these are going to be in scientific notation for the most part. If you have a very big exponent on 10, that means you're going to have more products than reactants. So that means what we say is the forward reaction is favored. Okay, and if you have a very small k, for example, here we have -30, that means that the reactants are much higher in concentration than the products, so the reverse reaction is favored. And sometimes you might even see that just such a small amount of products is made that we often say just no reaction, but our equilibrium position would be very far to the left or something like that. But if you see a small k, then the reverse reaction is favored. So when the significand of both, you're going to have something in the middle. So your exponent would be around 0, 1, -1, something like that. So let's talk about the equilibrium constant before we get into actually showing you how to calculate it. So the constant is unique to each reaction, and it doesn't matter how much of any of the substances you start with. The ratio can be reached by either going forward or reverse. So even if you start with only products, you can still reach equilibrium. Okay. The only thing that it does vary with is temperature. So you'll often see at 298 Kelvin, K equals blank, okay? Or at 900 Kelvin, K equals blank. So you'll see that temperature because K will vary with temperature. And that's the only thing it varies with, okay? It doesn't depend on the amounts. It doesn't even depend on a catalyst. Now, if you have a catalyst, you know that the reaction is going to happen faster. So equilibrium will also happen faster, but it's going to be at the same place. Okay, so if we have the concentration time graph here with a catalyst, so this would be the products, this is the reactants. With the catalyst, you get to that point faster, that equilibrium point, but here it's going to be the same number. All right, so let's talk a little bit about position versus the constant itself. Okay, so for any particular temperature, as we said, temperature is the only reason it varies. K is going to be the same for that reaction. But there are an infinite number of different concentrations that could get there. Okay, so equilibrium position is different from the equilibrium constant. Equilibrium position, if we were asked that, which you really won't be, but if you hear that phrase, it's talked about, we mean the concentrations, okay? So for example, if we use this, and I'm going to show you how to set these up in just a minute, but if we use this, you would have a concentration of 5, 2, and 2.5 to equal 4. But if this was the same reaction, you could have totally different concentrations, but they would still equal 4. So the idea here is that no matter what concentrations you have, you're going to have the same constant. So the reaction will fix itself to get to this equilibrium constant. So let's take a look at a reaction. Okay, we're going to do 4 different versions of this one reaction to kind of show you what it means. So in this first one, we are starting with 1 molar of HI. Okay, so that's the concentration of HI, and we'll talk about this later as well, but concentration is shown with brackets. Okay, so we start with 1 molar HI, and we have 0 H2 and I2. So this is what it will look like as it reacts. The question off to the side, from the graph, how can you tell that this reaction reaches equilibrium? And the answer to that is because the concentration lines remain constant up to a point. Okay, so at any given point, you're still having HI decompose, and you're still having H's and I's synthesize, but the forward and reverse reactions are the same. Until they reach equilibrium, you can see that the concentration of the products is going up and the reactant is going down because we started with only the reactant. So again, the answer here, how can you tell that this reaction reaches equilibrium? The concentrations of all substances remain constant. So that's what you would be looking for on a graph to see when equilibrium is reached. Okay, so here you can see we have the same graph here so that we can compare, but that's not the one we're talking about, so it's a lot lighter. So here, we're doing the opposite. We're starting with 1 molar each of H2 and I2, and none of HI. So in this one, over here, we only had the reactant when we first started, so at time 0 right here, before any reaction happened, we only had the reactant. So that went down, and then the products started forming until they reached this equilibrium, right? Now here, at time 0, we only have the products. So the opposite's going to happen. The products are going to go down as the reaction happens, and the reactant will go up because we need to create some of it. Now, we eventually hit equilibrium, which we know because then the concentrations remain the same, but those concentrations are not the same that we had before. Okay, and we're going to talk about that in the second part of this video. So right now we're just focusing on the graphs and how you can see that equilibrium will be reached, and it kind of takes a different path. So in the first one, we were doing the forward reaction because we started with only the reactants, which is usually what you think about in first year chem. In the second one, we started with only the products, so we were doing the reverse reaction. So you can see that either way, we eventually reach equilibrium. Okay, so here's our third experiment. So you can see the first one under here and the second one. Okay, here we're starting with 1 molar of all 3. So at our time 0, before any reaction happens, we have 1 molar HI, 1 molar H2, and 1 molar I2. So the question here is, when this reaction starts, does the reaction move forward or does it move backward? Which one is happening here? Okay. The answer is that the reverse or backwards reaction is happening. And we can tell that because the concentration of the products is going down and the concentration of the reactant is going up. So if we're using up this and making this, we're going backwards. But just like the other two, you can see that equilibrium is eventually reached. Different numbers. Okay. So if we look at a fourth trial, same reaction, but this time we have these random numbers, 0.3 molars of H2, 0.8 molar of I2, 0.5 molar of HI. So they're all starting at different places on our time zero, okay? And then we have equilibrium reached here at TE. That TE just means time of equilibrium. And then we have all these straight lines, but with these different molarities. So the question here is, what can you say about the equilibrium quantities in all four trials? We can see that they are all different, right? Equilibrium quantities means concentration. So equilibrium quantities here are all different, but they're going to fit the same constant. Okay, so let's talk about what that constant is. So if you want to put an answer here, you can say all different, but same constant. Okay, so let's start talking about K. K or KEQ is a generic term. It can be anything. So you'll see if people aren't specific, they'll just say K. But sometimes it's very helpful for us to say which K we're talking about, okay? We're going to focus for the first part of this unit on KP and KC. So KP is pressure, and we use atmospheres for pressure here. And KC is molarity, concentration. So C, concentration, P, pressure. KSP, we're going to do later on in this unit. And then next unit, the acid-base one, is where Ka, Kb, and Kw come in. So we'll talk about all of those as well. So here's when we talked about the square brackets. So square brackets of parentheses. You want to be careful about this on your free response questions because you can get these wrong. Like you get the whole expression wrong if you use the wrong one. Okay. So if you're asked to find Kc or you're given molarity in the problem, you want to use square brackets. But if it's Kp or you're given atmospheres in the problem, you must use parentheses, okay? And I'm going to show you how to write the expressions now, but that's kind of important because you're going to get so used to writing these expressions, it's going to be very second nature to you. You want to make sure you get the points and you don't lose them just for using the wrong little things to enclose them, okay? So make sure you're using square brackets for concentration and parentheses for pressure. Okay, so let's start writing our equilibrium expressions. So in equilibrium expression, a generic form of it is K is going to be the products over the reactants. And if you have the same, like if you have more than one product or more than one reactant, you multiply them together. Okay, so products would be multiplied and reactants would be multiplied. Now in your expression, you can just show that by sticking them together. You don't have to like write a multiplication sign. So here for Kc, we're going to take the concentration of NO. So I use my square brackets because it says Kc. So NO, and you don't really need to put the gas unless you really want to. And then this coefficient becomes an exponent. And then we're going to multiply that by the concentration of Br2. Subscripts stay with their substance, okay? So the 2 will just stay with Br, but the coefficients become exponents. So when we do these out, we're going to square the concentration of NO here. And then on the bottom, you put your reactant. So here we're going to have the concentration of Br NO. And that's also squared because that 2 goes there. So this right here is your equilibrium expression. So let's do the same thing for B, where this time we're doing Kp. So Kp equals the pressure of SbCl3. So I'm going to use parentheses, and I'm also going to put a P here, and then the substance under here. You'll notice I didn't have to put like C or anything up here because the square brackets already mean concentration. So for P, you're using parentheses, and you have to put the pressure thing there because parentheses could mean anything. So then here, we're going to do P of Cl2. And then on the bottom, we do P of SbCl5. And we have no coefficients in this reaction, so we have no exponents either. And that's writing the equilibrium expression. So you might see, and we're going to talk about this as well, get some more practice with expressions, you only include gases or solutions. So you don't include liquids or solids because their concentrations are constant. And you should never even put them there, okay? They do not matter. So if you have a reaction with some gases and some liquids, you would only put the gases. So let's talk about what that looks like. These are what we call heterogeneous reactions. That just means there's some solutions, liquids, there's some solids, there's some gases. That's all that means, okay? So in your expression, you don't have to put the states of matter, but what we will do is leave them out of the expression entirely. So this just says write an equilibrium expression. So we're going to do Kc for all of them. Okay, so for A, we're going to take our products. So we have HCO3 minus times OH minus, and then our reactants are going to be CO3 2 minus. Because H2O is in liquid form, we don't have to include it in our expression at all. And then for this one, I'm going to do it down here. We have the concentration of O2 to the third power, because that's a gas. But since this is a solid and this is a solid, that's all we have. Okay, so we don't even need anything on the bottom here. I'm going to rewrite that so it looks a little more normal. So our expression would just be O2, concentration of O2 to the third power. That's it. And then for C, we do concentration of Zn2 plus, concentration of H2 over the concentration of H plus squared because of that 2 coefficient. So make sure when you're writing these expressions, you're paying attention to the states of matter because they don't matter, They don't matter very often, but in here they definitely do. So this slide is just to show you that there's no units. It kind of goes through all the different situations that you could have and what those units would come out to be. For every unit, for every K, they would be different. It doesn't matter. They don't mean anything. We could go into why, but it just really doesn't matter. Okay, so your number does not have to have a unit on it. And then I wrote here the two other things that we'll be using this year, absorbance and pH. We also don't write units on, excuse me. So for a unit, don't worry about it. You do not have to have a unit on it. All right, so that's K. For the second part of this video, we're going to talk about how to calculate K. Okay, now we know how to make an expression. Let's talk about what you do with actual numbers. So we're going back to our 3 experiments because we asked, what could you say about all of the concentrations? And we said they're all different numbers, but they will have the same constant. Okay, so let's talk about that. So while HI is larger than H2 or I2, there doesn't seem to be any other relationship, but there actually is, okay? And that's why we just learned about the K expression. So equilibrium constant, all right? If we write the equilibrium expression for our reaction here, we would get Kc, we're going to write Kc, KEQ, you can write that too. But we have the concentration of H2 times the concentration of I2 over the concentration of HI squared. Okay. So here, if you plug in all those numbers, the HI, the I2, I wrote them here. If you plug them all into this expression, you get these numbers. And you can see how close they are. Okay, these are experimental values, so it's not going to be perfect. But these are very, very close to each other. So the KEQ is smaller than 1. What does that tell us about the extent of this reaction? Now, it's not super smaller than 1. So remember, we said if it's like super smaller, there might even be no reaction, like exponent's -30. The exponent here would just be -2. So it's not like super tiny, but it does tell us that the reverse reaction or the reactants are favored. And you can also see that in the graph because on every single equilibrium, like after it hits equilibrium and becomes constant, HI is higher. HI is the reactant. So you can see on there that reactants are favored here because every time, no matter where they start, even the one that we started with only products, you still end up with more reactant in the end. So you can see that by the graph and by the K value. All right, so this is just a slide to show you what you cannot do, okay? So here I used some common mistakes on K expressions. So here we forgot the exponent on HI, okay? We didn't change the coefficient to an exponent. So here, that's what that is. And you can see that those numbers, when you don't do that, are very far apart. They're not nearly as close as these are, okay? These are pretty much the same. So these are very far apart. And then here, what I did was I added the concentrations instead of multiplying them. And so again, you can see that doesn't work. Okay, so this is just some examples of common mistakes you might see in writing K, forgetting the exponents or adding the things when you need to multiply them. All right, So now let's do a quick, easy one just to get familiar with this before we start making it a little bit harder. So this one says, calculate Kp for the following reaction given the equilibrium quantities. So first thing we're going to do is write our Kp expression. So we have the pressure of SO3 squared over the pressure of SO2 squared times the pressure of O2. And because O2 doesn't have a coefficient, we don't have to have an exponent for that one. So now I'm just going to plug in these numbers they gave me. So the pressure of SO3 is 12. And then the pressure of SO2 is 2. And of O2 is 3. So when you do that out, you get 12 is Kp. I'll be honest with you folks, this probably isn't going to happen very often that you get a nice, easy problem with like this. Maybe a multiple choice, which is great because you can just do it real fast. That didn't even take us 90 seconds, and then we move on, okay? What's more likely to happen, especially in the free response, is this situation, okay? So you can read through this question. It's telling us NH3 is placed in an empty flask with a pressure of 3 atmospheres. So this is going to be the initial pressure of NH3. And it is allowed to decompose into its elemental gases. At equilibrium, the possible pressure of nitrogen of N2 is 0.25 atm. Okay. So here's how you would do a problem like this. This is not supposed to be there. Ignore that. So here is the reaction that is explained. You have NH3 and it decomposes into N2 and H2, and then to balance it, you write those things there. So now let's write the equilibrium expression. Okay, we're given atmospheres, so we're going to be writing Kp. So we would write our pressure of N2, our pressure of H2, third power, and then our pressure of NH3 squared. So that's going to be our equilibrium expression. The problem is we don't have these numbers. We have one of them. Nitrogen is 0.25. Okay, so that's going to eventually go in here. But we need to use our reaction and our knowledge of stoichiometry to figure out what the other pressures are at equilibrium. So we use something called a rice box. Okay, it's called a rice box because it says rice. This stands for reaction, initial, change, equilibrium. So you can see that I wrote the reaction here. And again, we have that stupid little symbol that doesn't mean anything. So you're going to write the reaction there. And then we're going to use these columns here to keep track of what's happening in the reaction. So let's write down what we know. We know that we start with NH3 only, and it's at 3 atmospheres. So I'm going to write 3 atmospheres right here. And since we only have NH3, it says NH3 is placed in an empty flask. We have none of N2 and none of H2. You can write 0 or whatever works for you there, okay? Then we find out that at the end, when we're at equilibrium, the partial pressure of nitrogen is 0.25. So remember our E stands for equilibrium, so we'll put this right here. So that means the change, if we went from 0 to 0.25, the change was we added 0.25. And if you don't want to have the units there because it's confusing in your rice box, that's fine. All right, so now we need to figure out all this other stuff. This is where your stoichiometry comes into play, okay? If we formed 0.25 of N2, if we use our coefficients, we can see that for every one N2, we formed 3 H2s, right? So here, we're going to take our 0.25 and multiply it by 3. Because again, for every one N2, we form 3 H2s. So instead of the change being 0.25 here, it's going to be 0.75. So all on the change line, you need to be using the reaction. That's where the change line comes from, okay? You have to kind of figure out all your other stuff, but then the change line comes right from the reaction. So let's take a look at N2 and NH3. In our reaction, for every one N2, you use up 2 NH3s. So again, if we have one N2, we needed 2 NH3s to get there. So here, if we have 0.25 atmospheres of N2, that means we had to use 0.5 atmospheres of NH3. Now you'll notice I added a minus sign here, okay, and a plus sign here. That's because we only started with this, so we know that some of it needs to be used up to make the products, right? Like in some of our other examples, we started with this, so we could have minus here. So you do have to think about like what's happening in the actual reaction here. So we had this, so we had to use up some of it to form our products. So now we have 2.5 atmospheres here. We already knew we had 0.25 there. And we have 0.75 here. So now we do have equilibrium concentrations. Or excuse me, pressures. Now we can just plug it into here, just like we did on that nice easy one that I said you'll probably never see on the AP exam. So now we just take Kp, we take our equilibrium expression, and plug in our numbers. Our H2 is 0.75, and that's to the third power. Our N2, 0.25, and then our NH3 is 2.5, and that's to the second power. So when you do that out, this is going to be your Kp for this reaction. So one more thing we want to talk about before we kind of leave this rice box equilibrium situation. Make sure you're reading the question carefully, okay? And that's the name of the game with AP as well. You don't want to lose points after doing all of this work because you didn't read it carefully. So make sure you pay attention to what it says, okay? So if you have something like this, where the molarity concentration is 0.5 initially, and after equilibrium is reached, 30% remains. Okay, so if you have 30% remains, you take this, multiply it by 30%. Whoops. And you end up with this. So that's how much remains. However, they also might write them like this. There is 0.08 moles of some molecule in a 200 milliliter flask. 40% of the molecule has reacted. What is the concentration at equilibrium? Okay, so in this case, you're going to take the moles, and you're not going to multiply it by 40% because that's how much reacted. We're looking for how much is left over. Okay, so we're going to multiply that by 60% because that's how much is left. We're also looking for concentration, so we're going to divide by the liters, 0.2. And that comes out to 0.2 full molar. So you want to make sure you're paying attention to what the question is asking. If it says remains, then you would just multiply by the percentage they tell you. If it says reacted, multiply 100 by 100 minus that percent. So let's take a look at a problem that could be written two ways. So this is the same problem, okay? 4 moles of gaseous NO2 are placed in a 1 liter container maintained at constant temperature after equilibrium was established, and this is where it's different. It was, for the first one, it says 25% of the NO2 remains, and here it says 75% of the NO2 had dissociated or reacted, and they want you to find Kc. Okay? So both of these problems are going to be solved the same way. So I'm going to go through how to solve it. I'm not going to change what I do, just make sure you're reading correctly. So I'm going to start by writing the reaction. And you'll notice I'm using my equilibrium arrow, goes in both directions. You also might see sometimes it written like this, but the 2 half arrows on top of each other is more common. And now I'm going to use my rice box. Okay, rice boxes are very, very helpful. We'll use them all the time. So this is going to be my R, my reaction. Initial, concentration, change, equilibrium. So wonky rice box. Okay. All right, so let's fill in what we have. So 4 moles of NO2 are placed in a 1 liter container. Because we're looking at 1 liter, the moles are the concentration, right? Because you would just divide by liters, and that's 1. So I can just put a 4 here. And if you want to put the capital M for molarity, that's fine too. After equilibrium was established, it was found that 75% of the NO2 had dissociated, or 25% of the NO2 remains. Either way, what we're going to do is subtract 3 here, because that's the 75%. It dissociated, right? 75% of 4 is 3. Or if you were reading it as the first problem, and it said 25% remains, you could just go ahead at equilibrium and write a 1, because that's 25% of 4. Either way, you get the same deal. Okay, so as long as you read the question carefully, solving this is going to be the same process. So now, once we have that, we go through and we do the same thing we did before. We're going to fill in. So we have no NO or O2 to start, because it's not mentioned at all at the beginning here. And our change is going to go from the reaction. So change goes to the reaction. So if we have a 2NO2 here, and we have a 2NO, that means the change is going to be the same magnitude, the same number, just different signs. So here we're going to add 3. But for our O2, our coefficient is a 1. So if we have 2NO2, and that makes 1 O2, that means we're going to cut that 3 in half. So here we'll add 1.5. So then we have 3 and 1.5. You can ignore this. That was just from the problem. Okay, so I'm going to write my equilibrium expression. NO to the second power, concentration of O2, over NO2 to the second power. Then I'm going to plug in my numbers. And that comes out to 13.5. So Kc is 13.5 for this one. All right, so that's it for this video. And we'll continue with equilibrium in the next one.